Good morning, afternoon, everybody. Um, yeah, so I have a few announcements before we get started because I always have a few announcements before we get started, but none of it is particularly surprising. Or I've already announced it anyway. So there is a couple questions on there on the screen. Feel free to get started on them, especially that second one. It'll take a while. Um, in terms of announcements, so everybody should have their tests back. So the Friday ones, you guys were sent your tests, I believe, on Friday. And if you have had the Monday tutorial, you were sent your test back yesterday. If you do have any questions about it, feel free to fire me off an email, or if you really want to set up an appointment time, you can do that as well. If you just want to deal with it in that way, that's okay too. That being said, because we sent back tests in this course and my other course, I'm a little backlogged on my emails. I will do my best to try and clear my way through them as quickly as I can to get to your emails if you have sent me something. So I'll try and get to those as soon as I can. I'll do my best to satisfy my 24-hour policy, but I have a lot of backup, so I'll just do my best on that one. Some people were mentioning test number 2, so test number 2 is in your next tutorial, depending on which day you have your tutorial, but it's in the next tutorial, and as such, it will cover up to basically the rest of chapter 1 that wasn't covered on the first test. That being said, math is cumulative, so you can't come back to me and say row reduction was on the first test, so it's not on this test. That would certainly not be the case. So officially, it is sections 1.4 to 1.7. 1.7, we're just finishing one example of that today, but grant all the important stuff of 1.7. We've certainly covered the ideas already, so that'll be the cutoff for test number 2, as I mentioned in an email I sent late last week, as well as on the announcements in UMLearn. I also sent an email on Friday with some important information. So if you did not read my email I sent late last week, please make sure you do so. It is very important because I want to make sure everybody is aware of the expectations. We let a couple things slide on the first test that won't be going forward, so just making sure that everyone is following and doing what they are supposed to be doing in case that becomes necessary. All right, let me scan through the questions. Adjoint matrices. Adjoint matrices is chapter 2, so no, it won't be covered on the next test. Will the things being covered today be included in test 2? The stuff in 1.7, but we're just doing this example. So effectively, this example might be on. But actually, I shouldn't say that. Anything that's on the test, we've covered already. So there's nothing that, anything that is being on the test, the next test will be stuff that has already been covered. So even section 1.7, we've covered everything already that would be on the test. Yeah, and I clarified that in an edit. So I did send out an email due to some issues that showed up on the first term test, reminding students that your webcams need to be on. What I meant to say was on during your tests. I think I said on during your tutorials. So the webcams have to be on during the tests. For tutorials that don't have tests, no, you don't need your webcam on. Everything in this course is testable. There's no, we're doing some of this, but not some of that kind of deal. Everything in this course is testable. Any tips on doing better on the next test? It's really hard for me to give general statements without knowing individual students. So I'm going to give a global answer that may not apply to particular students. And I'm giving an answer to 700 students, or I guess in this class, 170 students. So I don't want people coming back to me saying, I do that already. It's just like, well, I don't know you, what everybody's doing their study times. But for general ideas, what I found, especially in remote learning, distance learning situations through too many years of experience based on my hairline, is the fact that it tends to show up when it comes to online students, prevalent more than in person, online students where you're allowed to use your resources as students depend on that resources too much. And they say, well, I've tried the practice questions, but they tend to use their resources to do that. And all of a sudden 20 minutes is gone before they realized what happened. Right? So make sure, and again, some of you are doing it already, I'm sure, and it's not a magic bullet for everyone, but make sure that when you are doing your problems, you're not looking at your textbook to help you figure it out. I mean, at first, sure, but don't stop with that. If you can't do your questions without your notes, then you can't do your questions well enough. So making sure, and I say this in the course outline, you're allowed to use your resources, but if you're depending on them, your time's going to run out too fast. So making sure that you can do the questions without using your notes, without using the text. Sure, if you need to look up something really quick, fine, you're allowed to do that, no problem. But if you're looking up stuff throughout the test, those 20 minutes are going to be gone and you won't have a chance to finish. So that's what I find online students tend to have the biggest issue with, is they are not studying under the same conditions the tests are going to be. All right. Anyway, I can't promise everybody falls under that, but I find that that is the most global issue when it comes to remote learning tests. I didn't upload October 7th's class. Oh, my apologies. I'll make sure to get that uploaded as soon as possible after today. Yeah, so the structure, we haven't finalized the test yet, so I can't say for sure on the 3 questions, but the structure of the test, 20 minutes, that's going to stay the same. When is test 2? Your next tutorial. All right. So I'm going to give another couple minutes, get started on the questions that you're seeing in front of you right here. And yeah, I'll still have another, if people still have questions, I'll answer them for another couple minutes, but then we're getting to work. All right, so we have our matrix here. It's a 2x2 matrix, which means we can square it. You can only square matrices. I'll let you think about why that's the case. But how do we take a matrix and square it? That's right. We take our matrix, multiply it by itself. Careful, just like matrix multiplication is not just taking the entries. I said, the matrix multiplied by itself, just like the matrix, when we do matrix multiplication, we don't just multiply the individual entries. When we're squaring a matrix, we don't square the individual entries. And then it really just turns into another matrix multiplication type question where we would get, this doesn't look right. One minus 6, negative 5. 2, 6. No, that's right. All right, so it's just our matrix multiplied by itself. What was I thinking? Yes, that's what I was thinking. All right, so this is how we can square a matrix. It's not quite as annoying. For a cubed, how do we find a cubed? Yeah, it's a squared times a. I mean, technically it's a times a times a, but we've already multiplied two of them together, and so we can get a squared times a. So in other words, take our answer and multiply it by another a. Just like if you were doing 5 cubed, you'd go 5 times 5 is 25, and then multiply by another 5. I mean, multiplying matrices is more annoying, but the ideas are still the same. But it's useful. So 15 minus 36 is negative 21. Negative 6 plus 20 is 14. Negative 18 plus 40 is 22. All right. So any questions about how we can square, cube, any power of a matrix? Positive power, positive integer power of a matrix. All right, a question I get, and I got it in my other class, but no one's asked it here, so I'm going to ask it, is could we have done a times a squared? Well, for all of you saying yes, I thought multiplication wasn't commutative. I thought you couldn't change the order. Why is it different? I agree it's different. Why is it different here? Why is the order when we're squaring things different than the order for any other multiplication? Right, because we can move the brackets. The commutative property doesn't work, but the associative property does. So if you take this expression right here and you move the brackets, that is allowed. So the point being is no, matrix multiplication is not commutative. However, if all you're doing is multiplying the same matrix to itself, then the order in which you multiply the a with the a squared, or the a cubed with an a if you want to do a to the 4, that part doesn't matter. That one would be okay because technically it's a consequence of the associative property, not the commutative property. All right, so yeah, if let's say you did a times a squared instead of a squared times a, you should end up with the same solution. All right, what about a inverse? That's nothing new. What's our AD minus BC thing going on? Negative 4 plus 6, so that would be 1/2. So flip the main diagonal entries, so 4, negative 1. Negate the off-diagonal entries. So you could use, we have a method for finding the inverse now. You could roll with it. But it is a 2 by 2, so we do have that formula for it, and that's okay as well. All right, so here we have a inverse. The new question is, what do we do for a to the negative 2? Sure. If you want to augment it with the identity, there's certainly nothing wrong with that. But what do we do for a to the negative 2? So some people are saying it's a to the negative 1 times a to the negative 1. Sounds good to me. Can I combine these constants together? Switch the order of the constant multiple. Yeah, constants, we can do that, no problem. And then the rest of it is matrix multiplication. 12 minus 3, 9. Negative 8 minus 2, negative 6. Negative 6 plus 1, negative 5. Sounds good. What were you? I don't know. Can we? Some people are saying square it and then take the inverse. So what happened when we squared it? I already forgot what our answer was. Negative 5, negative 9. 6 and 10. So what's this? AD. If we use the formula, again, you could use the augment it with an identity and inverted thing, but we do have a formula for it. That'd be what? 1 over 4 AD minus BC. It'll be nice when I can call that what I really want to call it. And then what's that? 10, negative 5, 9, negative 6. All right. So, what do you know? We ended up with the exact same thing. So just a quick little note. People are wanting to do it both ways, so let me just confirm that. If you have a to the n, the inverse of a to the n, that's the same thing as the inverse raised to the power of n. And we call them, so since they're the same, it doesn't matter which one you do, and they're both just a to the negative n. It's actually kind of the opposite. We write it like this because the we kind of just could prove the exponent laws for this. So the nice thing is that yes, the exponent laws work for inverses just like they would have worked for real numbers, which is nice because why would we use the same notation if the rules didn't work? We should find a different notation otherwise. All right, beautiful. So any questions about how we raise things to powers, either negative powers, yay, negative powers, or positive powers? All right, integers though. Still sticking with integers. We're not going to do anything beyond integers. All right, so a to this random number that has no meaning, a to the 2021. This is technically premature. This is technically a bit premature, but it is something we're going to see. This is something we're going to see. What if we want to find the inverse of the inverse? What is the inverse of the inverse? That would just be the original matrix. Yeah, if you're given the inverse and you want to find the original, you take the inverse of the inverse to get back to the original. I think we did one example like that, but it was one of 100 examples we've seen so far. But we did an example like that where we had a matrix, we do the inverse of that, and then we wanted to get back to the original. All right, so a to the 2021. So we're just going to take a and multiply by itself 2021 times. Sound good? We've already done 3, so we're part of the way there. There actually are some ways of doing this without multiplying 2021 times. But there's a method for doing this that we're going to see a little bit later on. Is to take advantage. So there was another type of matrix here called a diagonal matrix. What was a diagonal matrix again? What did it mean to be a diagonal matrix? Yeah, all the entries off the main diagonal are 0. And what was really nice about diagonal matrices? A consequence of having all those zeros. What was really nice about them? I mean, they are symmetric, for sure. But multiplying them together was very easy. So what's 1002 squared? Yeah. This doesn't work in general, but for diagonal matrices, because of so many zeros, the zero stays zero, and we get this right here. What would be 1002 cubed? 1008. 1008. Multiplying diagonal matrices is super easy. All you have to do is multiply the main diagonal entries together and everything else stays zero. That's the magic of having a diagonal matrix. Unfortunately, A is not a diagonal matrix. So that's unfortunate. But diagonal matrices are much nicer to work with. You can multiply them easily, which means you can square them easily, take any power easily, because all you got to do is do the same thing to the entries. So here's what I want you to do. I want you to first verify that if we multiply together this right-hand side, we get the original matrix, and see if using the fact that A can be written in the form P times a diagonal matrix times P inverse might give us a way of taking powers of A a little bit more nicely. So I'll give you a few minutes to think about that. Maybe if nothing else, verify that if you multiply the right-hand side together that this is true. And see if you can think of a way of using this to get really big powers of A. P is a matrix. So P is this matrix right here. So P is just some matrix. D is some diagonal matrix. So for our example, I'm saying D is 1002. So really what I want you to do is just verify that what we're doing here is that this kind of identity is true. That if we multiplied out the right-hand side, that in fact is equal to the left-hand side. And then I want you to see if you can think about a way of using that to find powers of A. I don't want to explain it again. I want people to think about it. I will talk about it again, but I want people to think about, see if this might be helpful in some way to answer our question. Trying to make people think. That might play a role. We just have to make sure we're using it in the right way. That our matrix times an inverse is the identity will certainly play a role in this somewhere. We just have to make sure we're doing it in the right way. So does it matter, can I multiply these first two matrices together or the last two matrices together? Does it make a difference? No. What matters is the order. It doesn't matter which ones we do first. So if we did the first two, what are we going to get? 3, -2, -2, 2. Hey, we multiplied two non-symmetric matrices and got a symmetric matrix. That's interesting. All right, and then if we multiply these together, 3 times 1 minus 4, -1. 3 times 1 is 3 minus 6 is -3. -2 plus 4 is 2. -2 plus 6 is 4. And that is equal to A, which is our left-hand side. All right. So this part was not meant to be the tricky, complicated part. So it was just a matter of, so this is P, this is D, and this is the inverse of P. So in other words, what's the meaning of P? P is a matrix that works. There is no big meaning of P. P is just a matrix that works, and that's it. It's a magic matrix. I wasn't really supposed to be giving any significance to P. I mean, P is a matrix that made this happen, so it's not random, but P is a matrix that makes this happen. I mean, there could be a question about where P comes from. I don't want to think of it as magic right now. We'll talk about that at some point in this course, but for now, just wanted to let P just be some matrix that magically appeared. What I want to focus on right now is how do we use it? So let's say we had P times D times P inverse. So my question is, what is A squared? Some people are saying how to use this. Wonderful question. What is A squared going to be? That's going to be A times A. So what would happen if we took this right-hand side and squared it? So it's going to be P D P inverse squared. So that's true, but what does that turn into? I've still yet to see it correctly simplified as answers in the chat. No, not D squared. That would be nice. Unfortunately, it's not. PD squared P inverse. Where are people getting PD squared P inverse from? That's PD P inverse times PD P inverse. Okay. And what happens to this P inverse times P? Brackets aren't needed because we're associative. Yeah, that's just equal to I. Well, what about this? Isn't P times P inverse equal to I? And hence this is equal to D squared? Yeah, the order, right? They would multiply to give you I, but the problem is they're not next to each other, so even though that's a true statement, it's irrelevant because they're not next to each other. Otherwise, A and D would have been the same to begin with, and that wasn't true. So this isn't perfect. I mean, it would be nicer if it was just D squared. Unfortunately, it's not. But A squared is P times D squared P inverse. All right, what about A cubed? So that's P D squared P inverse. That's A squared. times another P times D times P inverse. Once again, the P inverse cancels the P, leaving us with PD cubed P inverse. What about A to the 4? P times D to the 4, P inverse, and so on. In other words, if we wanted to do any power of n, positive integer power of n, that would be P times D to the n times P inverse. Specifically, n equals 2021 for our example, but there's nothing special about 2021. It would work for any positive integer power. And if you actually took the inverse of that, it would work for negative integer powers too. All right. So, yay, we have a formula. That's nice. But why is this right-hand side better than this? To me, it looks like we're still taking a large power, and now we have to multiply it by two other ones as well. That seems harder. Or at least more work. Right, because taking a power of a diagonal matrix is a lot easier than taking the power of just any random matrix. So in other words, A to the 2021 is going to be D to the 2021 and now we can find a power of that diagonal matrix immediately. And so we really only need to multiply 3 matrices together as opposed to one matrix 2021 times. So that's the power of doing this. So this is called diagonalization. It's actually going to be something we'll talk a lot more about later in the course because there's some pretty big questions that we haven't been able to answer. I'll let you think about what those are. But the idea is if we can write it in this form, finding powers of A is a lot easier. And that is the big question. How do we figure out what P is if it doesn't just magically appear out of nowhere? Yeah, how do we find P? So we could finish this off. Let's just finish this off. So this would be 3, negative 2 to the 21, negative 2, 2 to the 2021. What is it? That's P right there. How did we get D? Same thing. Right. So this would be 3 minus 2 times 2 to the 2021. 3 minus 3 times 2 to the 2021. Plus 2 times 2 to the 2021. And same thing for the last. All right, so our big questions. How to find D. And how to find P. And not how do find D. How to find P. So these are obviously very big questions because you could spend more time than raising A to the 2021 trying to find these matrices P and D. Unfortunately, we're about 9 weeks away from doing that. But that is something we're going to see in this course, is how to find D and how to find P. So if you're really interested, feel free to take a look at Chapter 5. That's where we're going to see how to find P and how to find D. So technically, this is a bit premature. But if we have them, then this is a 1.7 question on how to use those matrices. The work to try and find those matrices we'll see later on. So for now, you would be given P and D. if you ever had to use them. But I promise you, by the end of this course, anybody who, anyone who's left by the end of this course, that's what we're going to do, is we're going to figure out how to find these matrices P and D. And also how to use this. I mean, okay, we know how to find large powers, but what use is that? And we'll do that as well. I hope so too. All right, that being said, wonky example aside, any questions about any of this chapter 1 stuff before we move on to chapter 2? Because there's been a couple students just wanting to say this word and I keep stopping them. Alrighty. Chapter 2. Determinants. Dun, da, da, da. So the idea is, when we were finding the inverse, there was this AD minus BC thing there. And so for those of you who've watched the pre-lecture videos, you'll know for a 2x2 matrix, that AD minus BC is something we call the determinant. And so what we're going to start doing here in section 2.1 is how do we find any determinant of any matrix. So let's make sure we're all on the same page. When I say find a cofactor, what is the cofactor of a matrix? How do we find that? Close. So I'm seeing some negative ones and random powers times some m thing. So let's say I wanted to find the cofactor of the first row, first column entry. So some people are saying -1 to the I plus j. So in this case, what's I and j? So I and j, I is the row number, j is the column number. Anytime we use I and j in this course, that's the row and the column. And then multiplied by what we call the minor. And what is the minor? How do we find that? How do we find that minor? Right, so if we want row 1, column 1, we cancel out, take away row 1, take away column 1, and then do what? We leave it with the determinant of what's left over. So a notational thing, if we're using vertical bars, then we're talking about a determinant, and a determinant is a number. If we're using squares, we're talking about the matrix. So square brackets would be a matrix. Vertical brackets means the determinant, which doesn't have anything to do with the absolute value. Some people use round brackets to also mean the matrix. So these are kind of synonymous. I'll stick with what we're doing here. But if you ever see square or round brackets, that's the same thing as the square brackets. It's referring to the matrix itself. People want to already jump to larger than 3x3s. We'll get to larger than 3x3s, but let's stick with 3x3s for now. We'll stick with 3x3s for now, although we'll come back to what to do if it's larger than 3x3. Right. And so what's -1 to the 1 plus 1? That's 1. And what's this determinant? So when it's a 2x2, we have a little formula for it. So what is the 2x2 determinant? All right, so that's going to be AD minus BC, just like the denominator when we were finding the inverse. The exact same thing. So for this matrix, what would that give us? That's right. I'll write it out. For the first one, negative 2 times 6 minus 5 times 0. In other words, that's negative 12. Right. So this is how we can find a cofactor. It's this little negative 1 thingamabob multiplied by the determinant when we eliminate a row and a column. And if that determinant is 2 by 2, then it's 2 by 2. How did we get the negative 1? Like, how did we get this? Yeah. Oh, so that's the definition of a cofactor, which I go over in the pre-lecture videos. Yeah, that's just the definition of what a cofactor is. It doesn't come from anywhere. It's part of the cofactor formula. Why it's useful will be something we see over time, but it's part of the cofactor formula. All right, so what changes when we go from the row 1, column 1 entry to the row 1, column 2 entry? Like most formulas get created, they get created from a need. So people wanted to do something that satisfied a certain property, and then a formula got created to make it work. All right, so first of all, if we find row 1, column 2, so that exponent changes from 1 plus 1 to 1 plus 2, which has its consequences. What about the determinant? What changes in the determinant? Instead of eliminating row 1, column 1, we instead eliminate what? Yeah, row 1, column 2. So if we're finding the cofactor in row 1, column 2, we eliminate row 1 and column 2. And that leaves us with 3, 5, 2, 6. What's negative 1 to the 1 plus 2? That's negative 1. And then 18 minus 10 would be 8. And we get negative 8. And that's how we can find the cofactor in row 1, column 2. What about row 1, column 3? What determinant would we be left with? Can't speak. That's right. Goodbye row 1. Now goodbye column 3. That just leaves us with 3, negative 2, 2, 0. Is it going to be the thing in front? Is it going to be plus or is it going to be minus? It's going to be plus 1. And then 0 minus negative 4 is 4. And so we get 4. And we could just keep going. We could keep going and find the cofactor along any row, any column entry. So in this case, we have 9 different cofactors we could find. And that is, how we could compute this. So any questions about how we compute these cofactors? Not quite. Close to that, but not quite. A little bit more to that formula. All right. So anyone happen to notice? Still no. Anyone happen to notice about this plus minus 1 when we change our entries? What's happening to that coefficient that's in front of it? It just oscillates, yeah? Plus, minus, plus. So some people, instead of remembering the formula, like to just remember, all right, in the first row, first column, it starts as a plus, and then it just alternates. Plus, minus, every time you switch a row or column, it just alternates plus, minus every single time. So instead of remembering a formula, not that there's anything wrong with the formula, exactly, a little checkerboard where you kind of have plus, minus, and so on. Then the next row is minus, plus, and so on, and it just keeps going. So if that makes sense to you, we can use that to remember, are we doing plus or are we doing minus? Otherwise, it's a formula. I mean, formulas work. Whatever makes the most sense to you. All right. So C21, is that going to be plus or minus? That's going to be minus. Now we eliminate row 2, column 1. Leaving us with 4, negative 1, 0, 6. So that's going to be negative 24. And I've lost my matrix. Just going to doodle it over here in the corner. (206). C22 plus or minus? Again, either checkerboard it, or negative 1 to the 2 plus 2 is negative 1 to the 4, which is positive. Eliminate row 2, column 2. Eliminate row 2, column 2. We're left with 16 or 12 minus negative 2 is 14. C23 plus or minus? Minus. Odd numbers negative, even numbers positive. Absolutely. So eliminate row 2, column 3. 2, 4, 2, 0. That's minus of negative 8, so that's just 8. And we just keep going. 3 more. C31 is plus or minus for C31? Yeah, back to plus. So that's 18. C32, now we oscillate. Goodbye row 3. Goodbye column 2, so 2, negative 1, 3, 5, which would be negative 13. And then back to plus, so on and so forth. Two, 4, 3, negative 2. Is that negative 16? I think that's negative 16. All right. So there's our cofactors. And the question for some random thing decided to give us the cofactor matrix. So negative 12, negative 8, 4. Negative 24. Apparently I can't remember more than one number at a time. 14 and 8. And then 18, negative 13, and negative 16. And let me just rewrite our matrix A, because we'll need it again. All right, so any questions about how we find any of these cofactors? Before we get to the kind of big reveal there at the end. All right, so there's our cofactor matrix. So let's find that determinant. There are benefits for finding all the C's that we're going to see over time. But if it was just a straight up find the determinant question, no, you wouldn't find all the C's to find the determinant. But there are other things that we're going to need all the C's for later on. All right, so when we say find the determinant by expanding along the first row, so what is the determinant of A? If we expand it along the first row, and I saw some people popping formulas earlier, so now let's pop some formulas. How would we find the determinant of A? Yeah, nothing easy is worth doing. Yeah, so that's going to be A11 C11 plus A12 C12 all the way up to A1N C1N, although in this case, there's just 3 of them. In other words, so it isn't just the cofactors, although the cofactors play a role. So that would be 2. Now we already have the answer, so I'll come back to that. But if we had, it would be 2 times the determinant, negative 2506, plus 4 times the negative of the determinant, 3526. Oh no, I paused it. And then plus negative 1. Plus negative 1. And then 3, negative 2, 2, 0. So I noticed some people, it was earlier on, but some people were putting a minus here. Some people were putting a minus here and alternating the signs in this formula. Technically, that's not true. It is plus every single time, although I can understand why some people were putting a minus here, because the minus would be part of the cofactor. So technically, we're adding the cofactor, but the cofactor itself is the negative of the determinant. So I'm sure a lot of you, as you get used to this process, if you aren't already, instead of writing plus 4 times the negative of the determinant, might just put the minus here, and that would, of course, would be perfectly fine. So this is how we can find the determinant. It's not just the cofactor, but the cofactor multiplied by the entry itself. So 2 times the cofactor. And then moving along to the 4, moving along to the negative 1. And then we get whatever it is. So that would be 2 times negative 12 plus 4 times negative 8 minus 1 times, what's that, 4, giving us negative 60. So this is how we can find the determinant. Somebody asked, do we need to find all the cofactors to do this? The answer to that is no. We would just need the appropriate cofactors for whichever row we're working with. Or column, but we'll get to that. All right, any questions about how we found the determinant using this first row? I think it's negative 60. Negative 24 minus 32 minus 4. Probably just some kind of a little arithmetic mistake. Why only the first row? So that's the definition of the determinant, is that we don't have to use the first row. We could use any row we wanted, but it's just one of the rows. Or one of the columns, and we'll get to that in the next example. All right, so I'll leave it to you. Try doing the exact same thing, but doing it along the second column as opposed to doing it along the first row. So I'll give you a minute or two to give that a try. So try and do this kind of computation, this type of computation, but use the second row times their cofactors. Why can't you use a calculator? Because I want to see if students can actually do this work as opposed to relying on the calculator to do the work for them. Negative 60? All right, well, let's try that second column. So our second column right here, again, I'll write out the matrix for myself just because I lose it off the top of my screen. Always keep forgetting that second one. So if we're doing the second column, so does the cofactor start negative or positive if we're starting in row 1, column 2? So we start negative. So negative 4 times the cofactor, well, the cofactor includes the negative, but 4 times the cofactor, which is negative. Then we move on to negative 2. So once we get the first one, whether it's positive or negative, then we can start to alternate. 2, negative 1, 2, 6. And then plus 0. Oh, plus 0. I guess technically it doesn't matter what the determinant would be, but we have it right there. Right, and so that's where the strategy, as kind of mentioned there in the chat, that's where the strategy is going to come into it, is if we're allowed to choose whichever row or column we want, then we might as well choose the one that has the most zeros. All right, so because it means less things to calculate. So why is it negative 4 instead of 4? So technically, the negative should be on the cofactor part of it. So again, it's negative 1 to the 1 plus 2, so we get the negative part of that cofactor. So again, you can write it like this if you want, but what I'll find is most students will, since the negative, it doesn't really matter where the negative goes, they'll just stick it out in front. All right, so that's negative 4 times its cofactor, which is 8, minus 2 times this cofactor, which is 14, and negative 32 minus 28, huzzah, is negative 60. So we get the exact same thing. And it can be proved. We're not going to do this proof in class, but it could be proved that it doesn't matter which rows or which columns we do. The answer is always going to give us the exact same thing. And that can be proved if you actually go through it and found all the little tiny pieces. And I do this in the pre-lecture videos where I write it out in all the little details, and you'll notice all the little tiny products are the same, just in a completely different order. But we end up doing all the same multiplications, they just are done in different orders, which is what makes them all the same. So in the videos, I go over more about why it doesn't matter which one we do, but from a computation point of view, we just do whichever one we think will be the easiest. And in my opinion, that's to do it along the row or column that has the most zeros. For example, here we only had 2 mini determinants to do. And that's how we can find determinants. So any questions about how we find determinants? All right, so I'm going to circle back to something someone asked before. So this isn't on my slides, but someone asked a question, what if we had something bigger? then a 3 by 3. What if we had a 4 by 4? There's a formula for 4 by 4s? That would be cool. What if we had a 4 by 4? What would we do? So this isn't an example, but this is just kind of a, I won't say aside because it is part of this. Right, so let's say we expanded along the first row. There's nothing, there's no zeros, so that's not going to be particularly nice. But what if we went along the first row? That's going to say it's 1. Eventually, yes, but not exactly right here. It would be 1 multiplied by what? Right, multiplied by C11. So eliminate the first row, first column, and we would get this. Okay. And then we move on. Move on to the 2. Again, we flipped it, so its cofactor will have negative. And then eliminate row 1, column 2, and take a look at what's left over. Then alternate again, plus 3. Goodbye row 1, column 3. So in other words, we do the exact same thing, it's just a lot more annoying the bigger the matrices get. But the ideas don't change. We still take the entry and multiply it by its cofactor as we go along any row, or if you chose a different row or different column, that's fine too. But if we started with 4 by 4s, what determinants are we left with? Good question. We'll get to that in just a second. But if we start with a 4 by 4, then what do our determinants become? 3 by 3. So how do we compute this determinant of a 3 by 3 matrix? Yeah, just like we did before. So in general, as long as you have enough time, you could find the determinant of a 6 by 6 by turning it into a bunch of 5 by 5s. And those 5 by 5s would turn into a bunch of 4 by 4s. And the 4 by 4s would turn into 3 by 3s, which would turn into 2 by 2s, where we could use the formula. So the idea is, yeah, okay, it might take some time, but we have this what's called a recursive process where we can always find the next size based on the smaller ones we'd have right there. How do we find a determinant of a 3 by 3? We just did that. That was our last example. The things that we got negative 60. The process that gave us the negative 60 was the determinant of the 3 by 3 we just did. Some people saying, do we have to do it on the test? Well, it depends. How many zeros are there? If there's a lot of zeros, then doing a 4 by 4 is not bad. Good question. Someone have an answer for that. Why did this 2 and this 4 have this negative in front? Great question. Why was there a negative in front of the 2 and the 4? Right, because the cofactor was negative. So here we had our cofactor was the positive of that determinant. Then we move on to the next entry, it becomes negative. Then move to the next entry, it becomes positive. Then move to the next entry, it becomes negative again. That's where those negatives came from. we'll get to special cases and stuff like that. We'll certainly talk about things like that as well as we work our way through this process. Yeah. I just won't start with special case. For example, like I don't want to start with special cases because something like that, we will do them, but if they only work for 3x3s and they don't work for 4x4s, then I don't want to start with that, because then people try and use formulas and random processes in places they don't actually work. So I want to talk about the process that will always work, and then we can talk about, oh, if it's this size, we can maybe do this. Right? So make sure the process makes sense to begin with, and then we'll talk about things that work in certain situations. Yeah, so we would do exactly for a 3x3, we would do exactly what we kind of did above right here. Bang. Whoops. That's how we would do it. So yeah, okay, unless you have a lot of zeros, doing 4x4s using this method gets really large in terms of number of computations. So we will talk about other methods that can work. Maybe there's some elementary matrices that might help us, and we'll see that along the way for sure. All right, anyway, back to the examples that I was talking about. So these are just things that we're going to see over time. So let's go back up to our matrices right here. So my question was, what would happen if we took the second row of A and multiplied it, first of all, by the second row of C? So what would happen if I just took the second row of A and multiplied it by the second row of C? So multiply the entries, add them together. What should we get? Straight up, multiply, add, multiply, add. What do we get? Someone said the determinant. Yeah, of course. It's the determinant. So we honestly shouldn't need to do the computations. What should we get? Unless I made an arithmetic error somewhere. Yeah, we would get negative 60. If we took row 2 times row 2, we would get negative 60. What if we took column 3 times column 3? What would we get? We get the determinant again, so we would get negative 60 for sure. The question becomes, and this will be useful in 2.3, but I wanted to preview it a bit. What would happen? So this isn't an obvious answer. This is actually do the computation. What would happen if we took the second row and multiplied it by the first row of C instead of the second row? What do we get? Get what? Negative 36 plus 16 plus 20. Gets 0. Interesting. Interesting. What if we take the second row and multiply it by the third row? We get 0. What about the third row times the first row? We get 0 again. So what would happen if we multiplied and took the entire matrix A times the entire matrix C? Oh, never mind. If we did C, we wouldn't be multiplying by the rows. We'd be multiplying by what if we did A times C? If we do A times C, we take a row times a column. So I don't really want C. What do I want? don't want C if I'm multiplying. I want C transpose. Okay, so what would A times C transpose look like? Well, they wouldn't all be 0, because what happens if we took the first row of A times the first row of C? What would we get? So A times C transpose would give us, well, if it was on the row and the same row in the column, so the diagonal entries, we get the determinant of A. And we get the determinant of A. All the way to the determinant of A. And what about, and off the diagonal, what would we get? Zeros. Yeah. Again, that's because when we took row 1 of A times row 2 of C, we got 0. Anything that didn't match was 0. Those would give us the off-diagonal entries. So a little factor job would say this is equal to the determinant of A multiplied by what? And if we divide through by A, we would get A times 1 over the determinant of A times C transpose is equal to I. What does that tell us? So put that together into a big idea. Yeah. The inverse is equal to 1 over the determinant of A times this crazy thing that we'll give a special name to later. But there's a value that can't happen. Yeah. So if the determinant of A is not equal to 0, then A has an inverse. And this is what the determinant will give us. I mean, it'll give us other things too, but this is the big idea that we'll get, is if the determinant of A is not equal to 0, then A is going to have an inverse. And the inverse is technically 1 over the determinant times the transpose of this cofactor matrix, which is actually something called the adjoint, but we'll talk about that a little bit more in section 2.3. So effectively, the same rule as 2 by 2's, a more complicated matrix to multiply by, but we would get that. Does someone have a good answer for that? Why did we need to take the transpose of C and not just use C as is? Why did we have to take transpose of C? Great question. Right. So when I was talking up here, we were saying the second row of A times the first row of C gave us 0. Or the second row of A times the second row or third row of C gave us 0. But when we multiply matrices, we take a row times a column. We don't take a row times a row. So that's why I wanted to transpose C so it is a row times a column, which is what matrix multiplication does. So that's why we took the transpose. So right, so if technically we haven't proven it, but yeah, something we are going to see a little bit later. Technically this doesn't prove it, but what we are going to see later is that the converse is true as well. So if the determinant of A is equal to 0, then A has no inverse. That is a true fact, although we haven't seen a reason why just yet. But that is going to be a consequence of something we're going to be seeing in section 2.2. All right, so this is how we compute the determinant, and also kind of the main idea of what we use the determinant for. So on Thursday, we'll spend a lot more time doing more determinants of other matrices, more examples, stuff like that. If you have any questions, let me know. If not, have yourselves a good day.